Can you see my presentation?
Yes, we can see your presentation and we can hear you.
Thank you, Doctor. Well, my name is Yanira Sánchez. I'm a PhD student in the University of Chihuahua, and I'm going to talk about mutarotation and solubility of lactose as affected by the presence of carrageenan. The cheese whey is a byproduct of the cheese making. It is of a great importance in dairy industry due to the large volumes produced and its nutritional composition. It is mainly composed of lactose and whey proteins, so it's a resource of a large number of valuable end products rather than a waste. Lactose is a disaccharide composed of galactose and glucose, and when it's in solution, it could change from alpha to beta lactose, and this phenomenon is called mutarotation. At 20 degrees, the balance of lactose mutarotation is achieved when the ratio of beta alpha isomers is 1.70, which means that there's no more change between alpha and beta. Is when the equilibrium is achieved. And we will have 62% of beta lactose and 37% of alpha lactose. Worldwide, 400,000 tons of crystalline lactose is produced annually. And in the food industry and the pharmaceutical industry has so many uses as the production of instant coffee, infant formula, baked foods, chocolate confectionery industry, and as an excipient of medicine. The industrial process of lactose crystallization from cheese whey is slow. It could take up to 48 hours and requires an elevated lactose concentration to induce nucleation, which implies high evaporation cost. Because the cheese whey has to reach a 65% of total solids, of which 56% are lactose. Lactose has to be in a supersaturated state in order to crystallize. Also, to modify or to improve the crystallization process, we can modify some properties of lactose, as the solubility and supersolubility point and the metastable zone. The metastable zone is this area that goes from the solubility point to the supersolubility point. And if we go through the metastable zone and over the supersolubility state, we reach the label zone where the nucleation is spontaneous and the crystallization could start. So there's some alternatives to improve the crystallization of lactose, as the use of antisolvents. Although it controls the crystallization process, it is not an eco-friendly solution because of the high amounts of antisolvents that are needed to reduce the solubility of lactose. Biopolymers of carrageenan has been studied because of their high water binding capacity that can control the crystallization process as well. The carrageenans are a family of linear sulfated polysaccharides that are extracted from red edible seaweeds. They show good ability to form gels with milk and water, and they are frequently used as a stabilizer, emulsifier, and food thickener. There's a variety of types of carrageenan, but we chose to work with iota and kappa carrageenan because of the stronger gels that they could form. They differ between each other in the content of sulfate groups. Iota carrageenan has the higher sulfate groups amount. In a previous work, the use of carrageenan to control the crystallization has been tested. And it's been reported that the addition of carrageenan could increase the number of crystals per milliliter, speed up the crystallization process, and they also reduce the mean size of the crystals. In this figure, we can see the control treatment and the treatment with the addition of carrageenan. And is evident how the addition of carrageenan makes more homogeneous the sample. We infer that these results are because carrageenan could control mutarotation and solubility, but there's no information about about this in the references. So our hypothesis is that the presence of biopolymers such as carrageenan will modify some physicochemical properties of lactose in solution, such as solubility, mutarotation, and supersaturation, which could have a favorable impact on lactose crystallization. Well, this work aimed to study the effect of carrageenans on lactose mutarotation and solubility, but why we want to modify the traditional process of crystallization? As I told you, it has some drawback, some disadvantage, and we want to increment the crystallization rate. This will lead to a higher number of crystals and a shorter size of the crystals. And we are also interested in a high purity of the end product. First of all, I'm going to talk about the mutarotation properties. To determine the alpha and beta lactose isomers, we use the an optical rotation method. The optical rotation were taken during 400 minutes at 25 degrees. And then where it was fed to an exponential decay function. And we also determinate the time to reach the mutarotation equilibrium. As I said before, the mutarotation equilibrium is achieved when there's no more change between alpha and beta isomers. Table 1 shows the effect of carrageenan on the effect of the time, the effect of carrageenan on the time required to reach the mutarotation equilibrium and the isomers of lactose. And it's been observed that the addition of carrageenan increment the alpha fraction and decrease the beta fraction, and it also decrease the time to reach the equilibrium. In the control treatment, I mean, without carrageenan, the time to reach the equilibrium is 5.5 hours at 25 degrees. This is similarly that Brackman in 2000s. They described that lactose solution at 18 degrees attained the mutarotation equilibrium in 6.5 hours. So with the addition of carrageenan, iota, or kappa carrageenan, we managed to decrease the time to reach the equilibrium from 5.5 hours to 2.5 hours. And we observed that the higher the concentration of carrageenan, the shorter is this time. The addition of carrageenans at any level or any type of carrageenan increase the fraction of alpha lactose and reduce the beta lactose. This has a positive effect in the purity of the end product in the lactose crystallization, because the presence of alpha lactose monohydrate that is less hygroscopic and is more stable is ideal for the pharmaceutical and food industry. With differential scanning calorimetry, we observed that there's no addition of carrageenan in the lactose crystals. You can see here in this figure how we only observe the peaks of alpha and beta lactose, and there's no addition of the carrageenan in the crystals. So the change in lactose mutarotation by carrageenans were probably the results of a modification in lactose solubility. It was a change in the water-carrageenan interactions rather than carrageenan lactose interactions. To determine solubility and supersolubility of lactose in presence of carrageenan, we made lactose solution and we add with or without carrageenan. Then they were maintained at constant stirring at 10, 25, 40, and 60 degrees and during 24 hours. Then after this time, they were filtered and vacuum dried, and we determinate solubility with this formula and supersolubility with this one. The supersolubility formula takes in account the solubility of lactose, its concentration, the alpha beta isomers, and this temperature-dependent factor. Figure 2 shows the change in lactose solubility by the presence of carrageenan. The dotted line is the control treatment, and we observe how the addition of carrageenan reduces solubility in all the temperatures and with both carrageenans, as well as the supersolubility has been reduced with the addition of carrageenan in all the temperatures. But both of the results were more evident at high temperatures. This is because in low temperatures, the carrageenans adopt an ordered state. When we apply a higher temperature, the carrageenans expose their sulfate groups and increase their water binding capacity. If the carrageenans will interact more with the water molecules, then the lactose will interact between each other, and it will be easier to reach the supersaturation state. Finally, we determine the metastable zone. As we can see in this table, the addition of carrageenan decrease the area in between the supersolubility and solubility curves that is called metastable. For the lactose treatment, the metastable zone is wider, which means that high supersaturation levels are required to induce nucleation, instead of with the addition of carrageenan that narrow the metastable zone, which leads an spontaneous nucleation and improves the crystallization process. Because how I said in the beginning of the talk, when we cross the metastable zone and the supersolubility point, we reach the label zone where the nucleation is spontaneous and the crystallization could start. Actually, the supersolubility point is called the driving force of nucleation. And the conclusions are that the addition of carrageenan in lactose solutions could modify the mutarotation equilibrium. The beta fractions were reduced and the alpha fractions were incremented, which has an impact in the purity of the end product. The time to reach the equilibrium was also reduced, and this has an impact in the time of the overall process of crystallization. I start telling you that the traditional process of crystallization of lactose is too long. It could take more than 48 hours. And we also managed to reduce solubility and supersolubility of lactose, as well the metastable zone. So these properties, solubility, supersolubility, and metastable zone determines the concentration of lactose required to start nucleation. If these properties decrease, then the nucleation and crystallization could start at a lower concentration, and this implies less extensive evaporation process and lower cost, which is so important for the industry. These are some of my references, and if you have any questions or criticize, thank you very much.
Is there any question for Yanira?
Yes, I have one.
Please go ahead, Ivan.
Hello, Yanira. At what scale are you doing your experiments right now?
It's a laboratory scale.
So, like, how much grams of lactose per liter of milk are you getting?
I was working in I start with 10% of lactose.
Okay. And do you have any plans to scale up this, or is right now your project is only
My plans in the beginning of my PhD were working with the whey protein, not the model solution. Well, I am behind my goals in this point because of the pandemic, but maybe I can apply this to this complex matrix. The results will be different.
Well, we can always do a postdoc as well.
Yeah, in New Mexico.
Yeah. Thank you very much, Yanira.
Thank you, doctor.
Any other question for Yanira?
Yeah, Yanira, I got lost a little. Could you explain what is mutarotation? I'm sorry.
Is when well, not only lactose, a variety of molecules, when they have isomers and they are in solutions, they change between each other, between alpha and beta lactose. And when they stop changing between each other, it's called that they reach the mutarotation equilibrium. There's no more changing. They don't alternate between each other. And with the addition of carrageenan, we saw that we could change this this equilibrium.
Sure.
Thank you, doctor.
Any other question?
Thank you, Dr. Delgado.
I do have a question. Did you use lactose solution on? Or
Yes.
are you planning to use whey permeate or whey or just whey?
That's why I was talking with the Dr. Ivonne Salmeron. That was a plan in the beginning of my PhD. I stopped working since March, so I hope I can go further and then I can work with whey protein.
Well, yeah, but there are essentially two different products. One is a whey, and it has a protein, or whey permit.
Without protein whey permit.
Okay, whey permit. If you do that, please take care of pH and acidity. That's the key when it comes to lactose crystallization.
Yes.
I mean, you have to characterize that part.
Yes.
Okay, any other question?
Thank you, doctor.
If not, I think we can move with the program.
Thank you very much.